to view stars which would be hidden from view. We know that gravity distorts time by virtue of the fact that if we take two identical atomic clocks and keep one at sea level and take the other one up to a high altitude, when we bring them both back together, they reflect different times. The difference in this passage of time is caused by the fact that a gravitational field weakens the further you get from the source. So the atomic clock which was taken to the high altitude was exposed to a less powerful gravitational field than the clock which we kept at sea level. The effect of a gravitational field on space-time is something that we've been able to observe, but not to experiment with. This is due to our inability to generate a gravitational field. And up until this point in time, great mass such as a star, planet, or moon was the only source of a discernible gravitational field that we're aware of. So just as the gravitational field around great mass such as a planet distorts space and time, any gravitational field, whether naturally occurring or generated, distorts space and time in a similar manner. Now the great benefit of generating an intense gravitational field is not only can you turn it on, but you can turn it off. If we refer back to our original illustration of space-time distortion, we can see that when we generate an intense gravitational field, we can distort the space-time and in turn the distance between the point where we are and the point where we want to be. We can then position ourselves at the point where we want to be and then stop generating the gravitational field, allowing space-time to return to its natural form. In this manner, we can travel great distances with little linear movement. And this is how space-time distortion translates into reduced distance. Now back to our original question, how is it possible to cross the vast expanses of space required for interstellar travel without exceeding the speed of light? This is accomplished by generating an intense gravitational field, distorting space-time and allowing you to cross many light years of space in little or no time and without traveling in a linear mode near the speed of light. The next question is, how do you generate a gravitational field? Up until this point in time, I've used the term generate to describe the capability of producing a gravitational field, but since I'm not aware of any way of creating a gravitational field from nothing, a more accurate term might be to access and amplify a gravitational field. And this is what I mean when I use the term generate. To understand how gravity is generated or accessed and amplified, you must first know what gravity is. There are two main theories. The wave theory, which states that gravity is a wave, and the currently accepted theory of gravitons, which are alleged subatomic particles that perform as gravity, which is total nonsense. Well, gravity is a wave, and there are two specific different types of gravity, gravity A and gravity B. Gravity A works on a smaller micro scale, while gravity B works on a larger macro scale. We are familiar with gravity B. It is the big gravity wave that holds the Earth as well as the rest of the planets in orbit around the Sun and holds the Moon as well as man-made satellites in orbit around the Earth. We are not familiar with gravity A. It is the small gravity wave which is the major contributory force that holds together the mass that makes up all protons and neutrons. Gravity A is what is currently being labeled as the strong nuclear force in mainstream physics, and gravity A is the wave that you need to access and amplify to enable you to cause space-time distortion for interstellar travel. To keep them straight, just remember that gravity A works on an atomic scale, and gravity B is the big gravity wave that works on a stellar or planetary level. However, don't mistake the size of these waves for their strength, because gravity A is a much stronger force than gravity B. You can momentarily break the gravity B field of the Earth simply by jumping in the air. So this is not an intense gravitational field. Locating gravity A is no problem because it is found in the nucleus of every atom of all matter here on Earth, and all matter anywhere else in our universe. However, accessing gravity A with the naturally occurring elements found on Earth is a big problem. Actually, I'm not aware of any way of accessing the gravity A wave using any Earth elements, whether naturally occurring or synthesized, and here's why. We've already learned that gravity A is the major force that holds together the mass that makes up protons and neutrons. This means the gravity A wave we are trying to access is virtually inaccessible as it is located within matter, or at least within the matter that we have here on Earth. However, the Earth is not representative of all matter within our universe. The residual matter which remains after the creation of a solar system is totally dependent on the contributing factors which were present during the creation of the solar system. This is true whether you believe that the origin of the universe was an evolutionary event or that a supreme being caused this event to happen. The two main factors which determine what residual matter remains after the creation of a solar system are the amount of electromagnetic energy and the amount of mass present during the solar system's creation. Our solar system has one star, which is our Sun, but the majority of solar systems in our Milky Way galaxy are binary and multiple star systems. In fact, many single star systems have stars that are so large that our Sun would appear to be a dwarf by comparison. Keeping all this in mind, it should be obvious that a large single star system, binary star system, or multiple star system would have had more of the prerequisite mass and electromagnetic energy present during their creations. This makes it possible for these systems to possess elements which are not native to the Earth. Scientists have long theorized that there are potential combinations of protons and neutrons which should provide stable elements with atomic numbers higher than any which appear in our periodic chart, though none of these heavy elements occur naturally on Earth. 88 of the first 92 elements on the periodic chart occur naturally on Earth. Some heavier elements do occur in trace amounts, but for the most part we synthesize these heavier elements in laboratories. Generally speaking, the stability of these synthesized heavy elements decreases as their atomic number increases, but experiments at the Lab for Heavy Ion Research in Germany have shown that this may only be true up to a certain point, as the half-life for element 109 is longer than that of element 108. The point is that our observations and theories are accurate. The fact is that heavier stable elements with higher atomic numbers which have more protons, neutrons, and electrons than any Earth elements do exist. However, up until this point in history, there has been no physical evidence to prove this. But now that proof is here. The most important attribute of these heavier stable elements is that the gravity A wave is so abundant that it actually extends past the perimeter of the atom. These heavier stable elements literally have their own gravity A field around them, in addition to the gravity B field that is native to all elements. No naturally occurring atoms on Earth have enough protons and neutrons for the cumulative gravity A wave to extend past the perimeter of the atom so you can access it. Even though the distance that the gravity A wave extends is infinitesimal, it is accessible, and it has amplitude, wavelength, and frequency just like any other wave in the electromagnetic spectrum. Once you can access the gravity A wave, you can amplify it just like we amplify any other electromagnetic wave. To demonstrate how a wave is amplified, we can use this oscilloscope, and as you can see, it graphically depicts the tone you hear as a wave. As we amplify the tone, you can see that the size or the amplitude of the wave increases, giving us a more powerful version of the same identical wave, and thus the tone sounds louder. In like manner, the gravity A wave is amplified and then focused on the desired destination to cause the space-time distortion required for space travel. This amplified gravity A wave is so powerful that the only naturally occurring source of gravity that could cause space-time to distort this much would be a black hole. This brings us back to our original question: how do you generate a gravitational field? You must have access to an element which is heavy enough for the gravity A wave to extend past the perimeter of the atom. Then you can access and amplify it for space-time distortion. To complete our 3 science lessons, the last question is, what is the power source for this type of travel? Well, for those of you with limited knowledge about power sources, I'm sure you can probably imagine the enormous amount of power required to cause a space-time distortion for this type of travel. After all, we're amplifying a wave that barely extends past the perimeter of an atom until it's large enough to distort vast amounts of space-time. For those of you with extensive knowledge about power sources, I'm sure it's probably even more puzzling as to how it's possible to have a compact, lightweight, onboard power source that can provide this much power. For everyone to understand that, I need to further explain a couple of things we briefly touched upon in the last question. If you remember, I said that for the most part, we synthesize or create heavier elements in accelerators, and their stability decreases as their atomic number increases. So what does this all mean? Well, we synthesize these heavier, unstable elements by using more stable elements as targets in a particle accelerator. We then bombard the target element with various atomic and subatomic particles. At this point, transmutation occurs, making the target element a different, heavier element. This element now has a higher atomic number, as the atomic number simply indicates the number of protons in the nucleus of the atom. So this is what I mean when I say their atomic number increases. What does their stability decreases mean? The length of time which an element exists before it decays determines its stability. Atoms of some elements decay faster than atoms of other elements, so the faster an element decays, the more unstable that element is considered to be. When an atom decays, it releases or radiates subatomic particles and energy, which is the radiation that a Geiger counter detects. As you can see, this Geiger counter is detecting the radiation from this uranium, which literally means that the Geiger counter is sensing the subatomic particles which are being released or radiated as the uranium decays. Those elements in which nuclear radiation can be consistently detected are radioactive elements. These heavy elements, which we synthesize in particle accelerators, are of the radioactive variety, and they decay very rapidly. Since we're only able to make a few atoms of these elements, and because they decay so rapidly, we're not able to observe much about them. This is what I mean when I say their stability decreases. However, there are elements with higher atomic numbers which are stable, even though they don't occur naturally on Earth, and we can synthesize them in particle accelerators. These are the elements in the 114, 115 range which don't appear on a periodic chart. Beyond element 115, the elements become unstable again, and in fact, element 116 decays in fractions of a second. This finally brings us to the power source. The power source is a reactor which uses this element 115 as its fuel. In this reactor, element 115 is used as a target and is bombarded with protons in a small particle accelerator. When a proton plugs into the nucleus of an atom of 115, it increases its atomic number and becomes an atom of element 116, which, remember, decays instantly. What element 116 releases as it decays, or what it radiates, is antimatter. What is antimatter? Antimatter is the exact counterpart of matter, which has a charge and a spin that is in the opposite of all matter. When combined with any matter in our universe, antimatter reacts and completely converts to energy. And remember, the rapid conversion of matter to energy is what we generally call an explosion. To demonstrate the explosive power of antimatter, let's pick a random area where an atomic bomb might explode. Oh, let's say Iraq. And for demonstration purposes, let's say an atomic bomb would explode, for instance, in, Baghdad. Well, if one of our older atomic bombs exploded in Baghdad, the area of total devastation, which is indicated by the red dot on the map, would be approximately 2 miles. This would be caused by a fission reaction in which less than 1% of the nuclear material is converted to energy. Most of you are familiar with the bombs that were dropped on Japan in World War II. This is the same bomb that was dropped on Nagasaki August 9, 1945. About this same time, Dr. Edward Teller, who's known as the father of the hydrogen bomb, figured out that a nuclear fusion bomb was possible. Fusion would release even more energy and cause an even bigger explosion from the same amount of nuclear material. Much to Dr. Teller's dismay, the Japanese surrendered, we never dropped the hydrogen bomb, and Dr. Teller's been in a bad mood ever since. But if a hydrogen bomb containing the same amount of nuclear material as the Nagasaki bomb were to explode in Baghdad, the area of total devastation would be approximately 20 miles. This would be caused by a nuclear fusion reaction, which again, less than 1% of the nuclear material actually converts to energy or explodes. The other 99% of the nuclear material on this type of bomb is dispersed, but is not involved in the actual nuclear fusion reaction. Now, if a bomb was made with the same amount of nuclear material as the Nagasaki bomb, and that material was antimatter, when that bomb exploded in Baghdad, the area of total devastation would include parts of Africa, Europe, and Asia, with the exact area of total devastation being very difficult to calculate. This would be caused by a total annihilation reaction, which is the complete conversion of matter to energy. 100% of the nuclear material on this bomb would explode or convert to energy. We currently have no practical way to harness antimatter into a bomb, and generally speaking, we can only isolate antimatter in a particle accelerator, and store it for a short time. This demonstrates the enormous amount of power released when you totally convert matter to energy, which is what happens when any matter and matter are combined. So back to our power source. Inside the reactor, element 115 is bombarded with a proton, which plugs